Let's go over how to solve a problem like the problem that was given in test 2. In the theory of relativity, time dilation is a difference of elapsed time between two events as measured by observers either moving relative to each other or differently situated from a gravitational mass or masses. So a clock set with respect to one observer may be measured to tick at a different rate when compared to a second observer's clock. This effect arises neither from technical aspects of the clocks nor from the propagation time of signals, but from the nature of space-time. So that was a little introduction to the problem. Note that you don't have to be an expert in space-time to solve this programming problem. It will come as no surprise then that time dilation also has a precise mathematical formula, and this is it. So when we're programming, we are going to implement this formula. Below is an example where we look at how time changes over 10 years traveling at a speed of 50% of that of light, 150,000 kilometers per second. Remember that the speed of light is approximately 300,000 kilometers per second. Because v squared over c squared is a ratio, we can either use the exact values or just the percentages of each value, so you can program it either way. It's easier in this case to do the latter. And then I give an example of how to do it with the exact values, and you get the same answer. So for a rocket traveling 50% of the speed of light, 8.66 years will pass for the rocket in the same time as 10 years pass for a stationary observer on Earth. So our job was to make a method that's going to calculate time dilation for a given velocity v and time t. We will assume c, the speed of light, is a constant of 300,000 kilometers per second, as in the example above. Here's what the header to your method is going to look like. And as promised, I gave you what your method header should look like. Note that we can determine what this method header should look like by looking at our equation. We're going to find time dilation, so we need to pass to the method the time, the velocity, and the speed of light. Note that we can know the speed of light, so we could hard code this into our method. But we will still need to know the time and the velocity of our rocket. So we're going to use this method to create a table that shows the time dilation for different velocities. The velocities that we're going to show in the table will start at 50,000 kilometers per second and go to 300,000 kilometers per second. And they're going to increment by 10,000 kilometers per second for every row. So in the second column, output the percentage of the speed of light of the velocity that's in column 1. So here's our velocity. Here's the percent of the speed of light. And then here's the output to our method, the time dilation in years that the rocket will experience. Okay, so let's first implement this part of our problem, and then we'll look at the rest of our problem. So open up Eclipse. I'm going to go ahead and create a new class. We'll write this from scratch. Remember to name your class names with a capital letter. And I can check the box to write main in my program. I'll click Finish, and I have my new program. Now, as always, you should write your name at the top of your program, and of course the date. And later on, we're going to write our algorithm up here. But it's good to think about our algorithm right now. And so the input to our program is going to be our velocity and time. And the output of our program is going to be a table that shows the velocity, the percent of speed of light of that velocity, and the time dilation of a rocket traveling at that velocity. All right, I think this is a pretty straightforward problem. We want to implement this method here, public static double time dilation with two parameters, double of time and double of velocity. All right, so now we just need to return a double. That's why it's red underlined. And so we're just going to return the equation, the result of our equation. And so looking at our equation, we have time multiplied by the square root of 1 minus v squared divided by c squared. So let's implement that. We can write that. Time times the square root. Now remember that you will need to use your math library to do this. And we want the square root of one minus. Now you can do v squared one of two ways. You could use your math.pow function. And the first parameter is our base. And so it will be our velocity. And then the second parameter is what power we are taking that to, our exponent. All right. And then we want divided by c squared. And we could hard code this if we'd like to. We could say 300,000 times 300,000. Now remember that you could also have used the math.pow function here as well. But just to show two different ways of doing it, I'll write it this way. We have our semicolon. And so now whatever they pass in as the time will be inserted into our equation for time. And whatever we give as an argument for velocity will be copied to the velocity parameter and then used in our equation. The equation will be figured out and then returned as a double. Now we can use this equation to write our table. So first write the header of your table. And looking back at what our table should look like, we have our velocity, our speed of light, and our time dilation in years. The next part of our problem is we'll want to print out a single row instead of a for loop, and then all subsequent rows will be printed in that for loop. So let's think about what we want in a row. We want our velocity, and we want it to start at 50,000 and end at 300,000 at increments of 10,000. We want the percent of that velocity, so this number divided by 300,000. And then we want our time dilation, which will be the return value of our function, given this velocity and the time of 10 years. All right, so here is our for loop. We have our I value starting at 50,000. This will be our velocity. You could have named him V as well. We have him being incremented by 10,000 on each loop iteration. And we have it looping until this Boolean statement is false. So we have it looping until I is less than or equal to 300,000. All right, so we just need to output our row. First part of our row is our velocity, which I called I. I then tabbed over 3. Then I concatenate that with a rounding of our velocity divided by the speed of light. course, this is a percentage, so that is why I had to multiply it by 100. And then I round that so it lops off the decimal places for me. I then concatenate that with a string with the percent symbol, so it'll look like a percent on my output. I then tab over 3. I then call my time dilation function, giving it the arguments of 10 for my time, and of course my velocity, which I called I, passing that into our parameter velocity. This would be a good place to test your program to make sure that your table is printing correctly. And as you can see in our output here, we have a table that looks like we needed it to. All right, so we see that we actually are not getting the correct output. It almost looks right. Looking back at our table, what it's supposed to look like, we can see that it should be a little bit less than 10 years. So when you get output that looks not correct, make sure you know what you're outputting so you can realize that this column should have been printing something less than 10 years. Now what did we do wrong? Our equation looks correct, and our error lies in our integer math. An integer times an integer is an integer. 300,000 times 300,000 is a large. I can look at the answer to this. 300,000 times 300,000 is 1, 2, 3, 4, 5, 6. So that's a million. This is a billion, so it is 90 billion. Remember that an integer can only hold about 2 billion, a little over 2 billion. So this number is too large for our integer, and so that's where we're getting this big error here. To fix this error, you can make one of our variables a double. You could have hard-coded we can make one of our variables a double, or, so this would fix our problem. See, our output looks a lot better here. Another way that you could have fixed this problem is by using that math.pow function. So when we use our math.pow, it returns to us a double, and it'll be the correct value. So when I run it this time around, I can also see, hey, those years look a lot better. Now I'd like to format this output to 3 decimal places. So I'm going to go ahead and create a decimal format object. I have a decimal format object here. I named it df. I use my new operator to instantiate this object. And then as a parameter to the constructor, I tell this object how to format things. So 3 decimal places. I'll put a 0.000. I also could have put a hash symbol in here, which stands for any amount of numbers. The 0 in the front, we'll put that 0 in the front down here so that it will print that 0 in the front. So now I need to use my df object, or my decimal format object. I'd like this time dilation, but its returned value to be formatted, so I can wrap this whole method call into my df format method. You can always think of a method as what it returns. So I'm formatting the double that returns from this method. I'll go ahead and run my code and see that my format and my output look awesome. Now it's on to making the second table. So our second table here is going to represent an astronaut traveling for 50 years at 50 million miles per hour to 650 million miles per hour at intervals of 100 million miles per hour. Here's what our table looks like. And so to make this table, in miles per hour in the first column and time dilation in the second column, we're going to need to make a method to convert our miles per hour to our kilometers per second. In order to use our time dilation method, we need to convert those miles per hour to kilometers per second. And I even wrote down the conversion for you. Here's what our method header is going to look like to convert the miles per hour to kilometers per second. So let's first write this method. Alright, so here's our method header. It returns type double. We named our method a really long but explanatory name of miles per hour to kilometers per second. We take as our parameter our miles. We then multiply those miles times the conversion factor. Then we return the results of that multiplication. So now we need to write our table to display our miles per hour and our time dilation. Alright, so we want to print the header for our second table first. We want to print this outside of our for loop, of course, because we want it to print one time. We then want our for loop to iterate. I'll call my miles per hour I, and I'll start him out at 500 million miles per hour. Now note that I made him a double because I know I'm going to get I really big really fast, and I don't want to have another problem of having an integer too large to fit into that memory location. Now I want to iterate until my velocity of I, which was in my miles per hour, is less than or equal to 650 million miles per hour. And I want to increment my velocity of miles per hour by 100 million miles per hour per loop here. Alright, I'm going to print out my row, so I'm going to print out my miles per hour, and then I'm going to tab over 3, and then I've already formatted this, but note that we can write this without the formatting at first. Now I want my time dilation with 50 as the amount of time in years, and then my miles per hour to kilometers per second. This will convert those miles per hour to kilometers per second so that it can be passed into this function call. Now note that I could have written this in 2 lines of code by writing it like this. And when we first start programming, sometimes it's better to look at it in 2 lines of code. But as we get better at programming, we'll want to write things like this with our 1-line code. So I'm determining my kilometers per second, so I'll make a temporary variable I call KPS, kilometers per second. But then I'm going to call that method miles per hour to kilometers per second, passing to it my miles, and it gives me back my kilometers per second. So then I can pass this variable to my time dilation method, and now he has the kilometers per second. Let's go ahead and run this code and see our output for our second table. I put a print instead of a print line, so I need to change that to print line. So then it will put an end of line character at the end of each row. And I can see I do get the proper output. It just needs to get formatted. Remember that I do not grade down for formatting, but it's good to see how to format this. We already have a format object that will format to 3 decimal places for us. So I can use that decimal format object that I created up here. And go ahead and call his format method. And he'll format to 3 decimal places for me. Go ahead and run my code and check that out. And now I'd like to format this column to go ahead and show all of its decimal places. No decimal places. So what I'm going to do is I'm going to make another decimal format object. Why not? So I'm going to go ahead and call him df2, and I'll have him formatted to no decimal places. So I don't even put the decimal point in there. Go ahead and save that. And if I would like him to then be formatted, velocity, I'll go ahead and use my df2 object on my format method. And now he'll be formatted with no decimal places. And that looks great. All right, on to the thinking question. So our thinking question read, now calculate how long it's going to take for an astronaut traveling through space to become older than their child. This is a classic twin problem. Assume the astronaut is traveling at 85% the speed of light, and when the astronaut starts traveling at this speed, she is 35 years old, and her child is 10 years old. Print out the number of years that it would take for the astronaut traveling at this speed to become younger than their child. And also print out both of their ages when this happens. So to solve this problem, we can use a while loop. Alright, so let's look at how to solve this problem. First, we're given that the speed that the astronaut is traveling is 85% the speed of light. So I'm going to go ahead and put that into a variable I call speed. I then know that the age of the sun is 10. I'm going to go ahead and put that in a variable. The age of the astronaut is 35, and this is going to be the count of the number of years. So what I'm going to do is I'm going to have my while loop iterate once for every year. So how long will I want to count? I want to count while the age of the astronaut is greater than the age of her son. Once the age of the sun becomes greater than the age of the astronaut, this while loop will end, and then I will know how many years that took. This while loop is iterating once every year. So I'm going to count every time that this loop iterates, and that'll tell me the amount of years. Now every 1 year, the age of the sun is going to go up by 1, of course. We all age 1 per year, 1 year per year. But since the age of the astronaut, or since our astronaut is traveling at this high rate of speed, she is not going to age by 1 every year. Every year, she's going to age by the number of years given back from our time dilation function. So we can call the time dilation function to know how many years she's aging for every 1 Earth year. So we can give the time as 1 for 1 Earth year, and our speed that we went ahead and put into a variable up here, 85% the speed of light. That's how much our astronaut is going to age per 1 Earth year. So I'll go ahead and run my while loop, and you can see that I output these things at the end here outside of the while loop. I can see that our astronaut ages by 0.52 years every 1 Earth year. So it takes 53 years for the sun to become 63, and the astronaut will then be age 62.9. All right, let's go over how to do the extra credit. So perhaps one of the strangest aspects of special relativity is that distances shrink in the direction of motion. This may not seem so important at first, but it leads to something quite remarkable. Common sense tells us that if a rocket travels at 90% of the speed of light, then it would take about 11 years to reach a star 10 light years away. And that is indeed what a stationary observer would see and measure. However, for the rocket, not only time but distance is going to dilate, and the star would be reached in only about 4.4 years. Going even faster reduces the time taken by an ever-increasing amount, and it follows the same equation as implemented above. For the extra credit for this test, we're going to make 2 more columns in the second table. The third and fourth column are going to hold the distance traveled by an astronaut in the 50-year time frame. Traveling at the first column's miles per hour. Note that the distance traveled will be different if you are an observer from Earth, which is our third column, than if you were the astronaut, which is our fourth column. So here's what our output's going to look like. Note that the last 2 columns are the amount of miles traveled as seen by an observer. So you can see that the observer sees that the astronaut travels a lot longer than the astronaut actually does travel. Remember our classic physics equation, distance equals rate times time? So in the last column, it is the astronaut's rate of travel and the astronaut's time. And note that these distances are in miles and that the time used in the calculation is in hours, not years. And these last two columns will be counted as extra credit, of course. So here's a hint. The number of hours in a year is 365 days times 24 hours a day. That gives us 8,760 hours per year. So this is hours per year. All right, let's look at how to solve. Okay, so looking at our for loop, we have modified it. And I went ahead and got rid of the ln here. This was important so that this third and fourth column would print in the same row as our first and second column. To start out, I go ahead and tab over 3. So here's our string with our tab characters inside of it so that I can print this third column. The third column is going to be distance equals rate times time. The rate that the human observer sees this rocket traveling is, of course, our velocity. Now our time is our 50 years, but since this is miles per hour, I need to multiply hours per year. That'll get rid of my years and also get rid of my hours, so then I'm left with miles. So distance equals rate times time. Same thing for our fourth column, distance equals rate times time. My rate is, of course, my velocity. Now my time is different for the astronaut. Remember that your time is your time dilation of 50 for the amount of time for the years, and of course my miles per hour to kilometers per second I have to call here for my velocity. And then I, of course, have to, since this is given back in years, I have to multiply by the number of hours per year to get rid of that years. And also now I have seconds per year. So this is my distance equals rate times time. And when I run this code, I can see my third and fourth column showing me my distance seen by an Earth observer and my distance traveled by the astronaut. And then the last thing I did here, of course, was I just rounded our outputs so that they will not show those decimals at the end. Alright, so that is a video on how to solve that test tube problem.